When we picture a severe car crash, our minds immediately go to the visible destruction.
Hmm.
We think about crumple zones folding up like an accordion, the shattered glass, the explosive pop of the airbags. But if you're in a modern electric vehicle, the most dangerous threat in that moment is actually completely invisible.
Right. Yeah.
It's a massive, terrifying amount of high-voltage direct current trapped inside the vehicle's nervous system. So today we're doing a deep dive into a highly specialized engineering document detailing the ASIL D standard. And our mission basically is to uncover this invisible 2-second war that your car fights to save your life the moment an impact occurs.
Yeah. And it really is a war. I mean, we are talking about hundreds of volts of raw electrical energy. In a crash scenario, that trapped electricity poses a fatal threat of electrocution to the passengers, and obviously to the first responders trying to cut them out of the vehicle.
Right, the jaws of life and all that.
Exactly.
Yeah.
You're in a massive risk of violent electrical arcing and explosive fires if that power isn't managed instantly. Yeah.
Okay, so let's unpack this, because I saw the phrase 2-second rule repeatedly in the source material. Why exactly 2 seconds? Like, where does that number come from?
So that is the absolute uncompromising automotive standard dictated by international regulations, things like ISO 26262 and ECE R100. From the exact millisecond the airbag triggers, the vehicle's electrical system has a maximum of 2 seconds to drain the lethal high voltage from the main system down to what is considered a safe level.
And what actually counts as safe when we're dealing with battery packs this huge? I mean, EV batteries are massive.
Right, they are. So the voltage needs to drop below 60 volts, or the residual electrical energy needs to fall under 0.2 joules.
Okay.
And it's a hard limit. If it takes 2.1 seconds to hit that mark, the system has failed the safety mandate.
Oh, wow.
If the voltage only drops to, say, 65 volts, it has failed.
I'm just trying to wrap my head around the physics here. How on earth does a car safely swallow that much lightning in 2 seconds while it's literally being destroyed? I mean, the car isn't just sitting in a quiet garage. It is in the middle of a catastrophic kinetic event.
You've hit on the ultimate engineering paradox of the electric vehicle. We are asking a machine to perform its most critical, delicate, high-precision safety maneuver at the exact moment it is undergoing maximum physical trauma.
Right.
So to understand the cure, we really have to look at the disease first. Like, how does a violent impact actively try to sabotage the car's ability to turn itself off?
Yeah, and the document spends a lot of time on something called root cause analysis. It basically outlines 4 distinct ways the car wants to fail during a crash. And the first one sounds kind of obvious but brutal. It talks about severing the nerves. How does a normal shutdown sequence even begin?
Well, in a normal, intact vehicle, your airbag control unit is hardwired to your motor controller. When the sensors detect a crash, the airbag unit fires off a signal saying, we've crashed, dump the power. But in a severe impact, the physical wires carrying that message can be sheared clean off. I mean, the connectors can be violently yanked out by the shifting metal.
So the brain of the car doesn't even know it needs to shut the power off. The signal just completely dies.
Exactly.
But the document also mentions something about EMI, electromagnetic interference. Does that mean even if the wire doesn't snap, the signal still might not make it?
Yeah, the sheer violence of a crash generates extreme electromagnetic interference. Think about heavy metal structures like the battery box or the vehicle frame, violently grinding and crushing together.
Right, yeah.
That friction and structural failure creates a massive broadband burst of electromagnetic noise.
Wait, crushing metal creates static, like radio interference.
Yes, it creates an intense electromagnetic field disturbance. It's like standing next to a massive radio jammer. So the critical shutdown signal from the airbag gets completely drowned out in this sea of electromagnetic chaos.
Oh, man.
The motor controller just can't hear the command over the noise. The safety chain is broken at the very source.
That is terrifying. But the second failure mode actually scares me more. The document calls it contactor welding. This happens when the car does try to shut off, but physically can't, right?
Yeah, we have to look at the microphysics of what happens in the milliseconds, right before the full physical impact is even realized by the occupants. In a severe crash, the crushing of components often creates extreme short circuits or massive overloads of current.
Okay.
And this generates a terrifying amount of heat inside the high-voltage system.
How much heat are we talking about? Like melting metal heat?
Literally melting metal.
Ah.
The high-voltage main relays, the physical heavy-duty switches that are supposed to spring open and cut the power from the battery to the car, they experience intense electrical arcing. The heat from that electrical arc literally melts the metal contacts together.
Oh, wow. So it solders itself shut.
Basically, yes. So the car's computer realizes there's a crash, it cuts the low-voltage power to the switch coil to let it spring open, but it can't move.
Because the switch has been welded shut by its own electricity?
It is mechanically fused solid. And because it's fused, the massive high-voltage battery pack stays perfectly connected to the rest of the vulnerable system.
Right.
The car then tries to trigger its active discharge circuit to drain off the energy. But instead of draining a small, limited pool of trapped energy, it's now trying to drain the entire main battery pack.
It's like trying to drain a swimming pool with a straw while a fire hose is still pumping water in.
That's a perfect analogy.
Wow.
The discharge circuit gets entirely overwhelmed by the infinite power supply and just burns itself up.
Okay, so the wires are jammed, the switches are welded shut, but the car is still physically crushing inwards. What happens to the actual circuit boards during all this? The source talks about physical mutilation and power sag.
Think about the immense G-forces involved in a high-speed collision. The printed circuit boards inside these control units physically bend and warp under the shock wave. When a rigid board bends, the solder joints holding the heavy, massive discharge resistors experience severe fatigue. They develop microcracks, or in many cases, the sheer force just snaps the components right off the board.
The hardware literally disassembles itself in real time. And at the same time, the document mentions the 12-volt battery usually dies.
Right. We refer to that as a power sag. During a crash, the car's regular 12-volt battery, the one that powers the computers, the airbags, and the safety chips, it often gets disconnected or crushed.
Oh, I see.
So the high-voltage system is still raging, but the low-voltage system that powers the gates and the switches needed to manage the high voltage has collapsed. The safety chips lose their bias voltage and just black out.
It's a cascading nightmare. The system loses its power to even think. But the fourth failure mode is the one that really blew my mind. The source calls it an MCU clock out. It basically implies a microchip can get a concussion. I didn't think solid-state electronics could get concussions.
It's a deeply misunderstood vulnerability of modern electronics. Microprocessors, the brains of the car, don't just run on their own. They rely on an external component called a quartz crystal oscillator.
What does that actually do?
Think of it as a microscopic tuning fork. Through the piezoelectric effect, this tiny piece of quartz physically vibrates millions of times a second when electricity is applied.
Okay.
That vibration gives the processor its clock speed, its sense of time, rhythm, and sequence.
So there is a literal physical object vibrating inside the computer chip.
A tiny physical structure, yes. During a severe crash, the high-frequency vibration and intense acoustic shock waves can physically shatter that microscopic crystal structure or cause its vibration phase to slip. The chip's heartbeat suddenly stops. Its phase-locked loops lose their synchronization.
It's like a runner who completely forgets how to run because their internal metronome just shattered into pieces.
Exactly. The processor gets trapped in what software engineers call a state machine trap.
State machine trap.
Yeah, the operating system is stuck in a continuous loop of whatever normal driving operation it was performing right before the impact. It literally has no concept of time advancing anymore, so it can never execute the command to jump to the emergency safety discharge subroutine.
Wow!
The physical car is crumpling into a wall, but the electronic brain is frozen in the moment, right before the crash, forever.
So we have severed and jammed communication wires, switches welded shut by their own heat, circuit boards snapping in half, total loss of low-voltage power, and a microchip with a literal concussion. And despite every single one of those catastrophic failures happening simultaneously, the car still has to guarantee a safe discharge in under 2 seconds.
Yes.
How do you even begin to build a defense against that? Like, what's the architecture there?
You build an architecture of extreme paranoid redundancy. The ASIL D safety standard demands it. Let's look at how the engineers construct this 2-second defense system. The document highlights a dual-channel communication setup.
Dual channel meaning 2 totally separate ways for the crash signal to travel.
Exactly. They refuse to trust a single pathway. Channel 1 is a physical, heavy-duty hardwire running directly from the airbag unit to a dedicated safety chip in the motor controller.
Okay.
And Channel 2 is entirely software-based, sending a high-priority encrypted crash message over the car's internal data network, like the CNFD or Automotive Ethernet. The system constantly cross-references both channels.
But wait, if the main brain is concussed and stuck in that state machine trap we just talked about, how does it process those signals, whether they come over a wire or a network?
It doesn't.
It doesn't.
No, the main brain is bypassed entirely. This relies on something called SBC hardware gating. SBC stands for System Basis Chip. The engineering specifications specifically mandate chips like the TLF 35584.
Okay.
This component is completely independent of the main microprocessor.
So it's reflexes over brains.
If we look at human biology, it's exactly like the reflex arc in your spinal cord that pulls your hand away from a hot stove before your brain even registers the sensation of heat.
Oh, that makes perfect sense.
Right. When that physical hardwire voltage drops during a crash, this independent SBC chip reacts autonomously in less than 100 microseconds.
Microseconds, not milliseconds. A tenth of a thousandth of a second.
It is nearly instantaneous.
Yeah.
It ignores the concussed main processor entirely. It instantly cuts the power to the main high-voltage relays to try and disconnect the battery, and simultaneously forces the physical discharge switch to open.
Okay, so it acts immediately.
Yeah, and this dumps the trapped high-voltage energy from the capacitors into a massive resistor, burning it off as heat.
Okay, I follow that. But let's go back to failure mode number 3. What if that massive physical resistor snapped completely off the circuit board when the car hit the wall? The system reacts in 100 microseconds, hits the switch, and, well, nothing happens because the pipe is broken.
The engineers anticipated that exact physical failure.
Of course they did.
Yet the safety system is constantly monitoring the voltage drop in real time. If it triggers the physical discharge resistor and sees that the voltage isn't plummeting fast enough, meaning the resistor must be broken, it abandons that plan and immediately activates the ultimate backup.
Which is?
Stator copper loss.
Okay, here's where it gets really interesting because the solution here is incredibly elegant to me. How do they weaponize the car's own motor to fix this?
Normally, an electric motor uses high voltage energy to create a rotating magnetic field that spins the wheels. But in this emergency backup scenario, the safety software performs a mixed voltage modulation.
Mixed voltage modulation.
Right. It takes all that lethal, trapped high voltage energy and violently injects it as a massive, perfectly symmetrical current directly into the copper coils, the stator, of the car's electric motor.
But wouldn't injecting massive power into the electric motor make the car suddenly lurch forward or spin the wheels while it's in the middle of crashing? That sounds incredibly dangerous.
It would be, but the brilliance lies in the symmetrical injection. They specifically inject what is known as a direct axis current.
Okay.
This creates opposing magnetic forces inside the motor that cancel each other out. It actively traps the magnetic field at a state of absolute zero torque.
Zero torque, so it can't move.
Exactly. The motor is magnetically locked and cannot spin no matter how much power you dump into it.
So all that raw electrical energy is being shoved into the motor, but it can't create movement. Where does the energy go?
It turns into heat. They are using the natural electrical resistance of the hundreds of feet of tightly wound copper wiring inside the motor as a giant makeshift space heater.
That is so clever.
They intentionally burn off the lethal electrical energy by intensely heating up the motor block itself. And this software-driven backup method safely drags the system voltage down below 60 volts in just 1.5 seconds.
That is just wild. They use the motor's own internal resistance to destroy the energy without turning the wheels. And what happens after they hit that 60-volt safety threshold? Is the car just safe to tow away? Once it successfully gets that voltage under 60 V, the system hits the absolute point of no return. It writes a permanent death code to its deepest non-volatile memory.
A death code?
Yeah. The technical document notes this as DTC P0A0D.
A permanent death code. Like you can't just plug in an OBD scanner and clear it like a check engine light.
No, it's irreversible by design. Once that specific code is written, the car can never, ever be turned on again. The system physically refuses to boot up the high-voltage contactors.
Wow.
The protocol requires a complete professional teardown by highly trained technicians to ensure the vehicle isn't a rolling fire hazard.
Okay, so that covers the theoretical architecture. It's a brilliant sequence of fail-safes. But having a great concept on paper is one thing. The literal physical components soldered onto the circuit board have to survive that 50G impact to actually execute this plan.
Right, they have to physically hold together.
So how do they design the physical board to not just shatter? Because earlier we talked about the boards bending and breaking. Right, so here we enter the realm of DFMEA, design failure mode, and effects analysis.
DFMEA.
Yes, this is the discipline where engineers proactively hunt down every microscopic way the physical design could fail in the real world, and they literally armor plate the layout.
The source material talks about establishing a safe core area layout on the circuit board. What does that actually look like?
Think about a rectangular circuit board bending during a violent crash. The edges of the board flex and bend the most. absorbing the kinetic energy.
Right, like a diving board.
Exactly. So the strict design rules, like DGPCS HW Day 005 mentioned in our source, dictate that every single critical component responsible for this 2-second discharge must be placed in the absolute physical center of the board.
The eye of the hurricane, basically, where the mechanical bending stress is at its absolute lowest.
Exactly. And they go much further than just placement. The engineers cut actual physical slits entirely through the fiberglass circuit board around this central core area.
Wait, they cut holes in the board?
Slits, yes. These slits interrupt the mechanical stress waves, preventing them from traveling across the board and reaching the safety chips. They also install rigid support pillars directly underneath the heaviest components to prevent them from ripping their own solder joints out.
Wow.
They are engineering the board to survive a 50G shockwave without a single microscopic fault line forming.
But physical shock isn't the only threat to a circuit board in a crash. There are electrical ghosts, too. The document mentions preventing ghost turn-ons by using a negative 5-volt bias and an active Miller clamp. I need an ELI 5 on this. What is an electrical ghost?
This deals with the extreme electromagnetic environment we touched on earlier. When you are switching high voltages very quickly inside an EV, it creates massive electromagnetic interference, upwards of 10 kilovolts per microsecond.
That's a lot of interference.
It is. That intense interference can actually interact with something called parasitic capacitance inside the tiny transistors on the board.
Parasitic capacitance, like unwanted static electricity building up where it shouldn't.
Think of it like wind catching a door. Every transistor has a tiny bit of natural, unavoidable capacitance, the Miller capacitance. The extreme electrical wind of a crash can build up enough charge to accidentally push the transistor's door open, tricking the switch into turning on when the computer is desperately telling it to stay off.
Oh, so a burst of electrical noise could trick the emergency discharge switch into turning on while you're just driving down the highway normally.
Yes, and it would instantly connect the high-voltage battery to the emergency discharge resistor. The resistor would rapidly overheat, melt, and catch fire while you were cruising at 70 miles per hour.
Which is obviously a catastrophic failure. So how do they stop the wind from blowing the door open?
To prevent these ghost turn-ons, the design applies a continuous negative 5-volt pressure, a negative bias against the switch's gate. They're actively holding the door shut from the inside with electrical force, combined with an active Miller clamp that physically shorts out any stray voltage buildup.
Okay, so it's a reinforced door.
Basically, the electromagnetic wind of a crash simply cannot overcome that negative clamping force.
That covers the physical bending and the electrical ghosts. But there's also the issue of the sensors just straight up lying to the computer.
Yes, thermal drift.
Right. The document has this hyper-specific mandate requiring Class 1 C0G ceramic capacitors. Why such an obsessive shopping list for what is essentially a thermometer?
Because maintaining precision in a chaotic, extreme environment is incredibly difficult. To know if the system has safely reached that critical 60-volt threshold, the computer has to measure the voltage accurately. But during a severe crash or an ensuing electrical fire, the circuit board gets violently and unevenly heated.
And heat messes with electronics.
Right. Standard electronic components change their physical behavior when they get hot. Their internal electrical resistance drifts.
So a cheap sensor might get hot and tell the computer, hey, we're at 50 volts, the discharge was a success, all clear, when in reality the car is still sitting at 300 volts, just because the sensor's internal math got sloppy from the heat.
That scenario is a lethal false negative. The computer stops the discharge early, thinking the job is done, leaving a lethal charge in the vehicle.
Yikes.
So the ASIL D standard mandates Class 1 C0G, or NP0, ceramic capacitors, and thin film resistors. These specific materials have virtually zero temperature drift. Their thermal coefficient is strictly limited to less than 25 parts per million per degree Celsius.
Meaning they don't change their physical properties no matter how hot they get.
It ensures the computer gets an absolutely bulletproof, mathematically pure voltage reading, even if the circuit board itself is literally on fire.
The level of paranoia in this design phase is staggering, but obviously entirely justified when lives are on the line. But a blueprint doesn't save lives. The actual physical object rolling off the assembly line does. Which brings us to the manufacturing side. What happens if a factory robot makes a tiny, almost invisible mistake?
This shifts us from design FMEA to process FMEA, process failure mode, and effects analysis. In the realm of ASIL D safety standards, good enough during the manufacturing process is considered a death sentence. The physical assembly must be mathematically perfect.
The document details this obsessive process of hunting for microcracks on the assembly line. They use 100% 3D X-ray, or AXI, and ultrasound scanning on the microchips right after they are soldered to the board.
Hmm.
And the rule is aggressively strict. Solder voiding must be under 5% total and under 1% for any single connection pad. Why such an obsession over a 1% air bubble in a tiny drop of solder?
I know a 1% void sounds incredibly pedantic, almost impossible to care about.
Yeah.
But you have to multiply that microscopic 1% air bubble by a 50G kinetic impact.
Because the physics change under stress.
Exactly. Under normal daily driving, a 1% void in a solder joint is perfectly fine. The electrical current flows around it.
Yeah.
But when the car hits a concrete barrier at 70 miles per hour, that 50G physical stress looks for the weakest point in the material to release its energy.
Oh, I see.
It concentrates completely around that microscopic air bubble.
The bubble acts like a wedge.
The physical stress instantly propagates that bubble into a microcrack. In milliseconds, the crack widens, severs the electrical connection, the emergency discharge circuit goes dark, and the rescue workers get electrocuted.
Just because of an air bubble.
Yes. So the manufacturing team has to aggressively hunt down and eliminate those invisible bubbles on the factory floor using 3D X-rays before the board ever sees a car.
And it's not just the delicate microchips they scrutinize, it's the heavy mechanical connections too. The high voltage bus bars, the thick metal arteries carrying the main power from the battery, they're bolted together.
But the factory doesn't just use a regular air gun or a torque wrench, right?
No, they use highly specialized servo-driven torque angle wrenches. First, every single high voltage bolt is specially phosphate coated to guarantee a highly specific friction coefficient.
And when the robotic arm tightens that bolt, it isn't just turning it until it feels tight. The tool is digitally recording the exact tightening curve, the precise amount of torque applied at every single degree of physical rotation for every single bolt on every single car.
I can't even fathom the amount of data storage that requires. Why do they need that level of granular data for a simple bolt?
To guarantee contact resistance, they need the physical connection between those two thick metal plates to have an electrical resistance of less than 5 microohms.
Microohms. Almost perfectly conductive. What happens if it's slightly looser than that?
If the bolt is even fractionally loose, the resistance at that joint increases. During a crash, when the system tries to forcefully dump massive violent amounts of electrical current through that joint to drain the battery, that slightly loose connection acts like a bottleneck.
And a bottleneck creates friction.
Electrical friction, which is joule heating. The formula is power equals current squared times resistance. Because the current is massive, even a tiny increase in resistance generates localized extreme heat. Yeah, a loose bolt will literally glow red hot, melt itself, sever the heavy-duty connection, and fail the 2-second discharge.
It's wild that they track the entire life history and torque curve of a single bolt just to guarantee it can survive 2 seconds of hell. And before any of these finished control units are allowed to leave the factory, they face the final exam.
The end-of-line, or EOL, test bench. Every single unit built must prove it works.
Every single unit gets hooked up to a massive automated rig that artificially fakes a crash. They inject the crash signal into the pins, and they measure the exact time it takes the hardware to drop the high voltage.
And the margin for error is absolute zero. The safety standard expects the physical discharge to occur between 1.2 and 1.5 seconds. If the computer monitoring the test bench sees the discharge take 2.01 seconds, or if it detects the voltage curve stuttering for even a fraction of a millisecond, the manufacturing execution software automatically flags it.
Does it go back for repairs? Like, can they just resolder it?
Absolutely not. It locks the product's digital serial number permanently and throws it in the scrap bin. There are no reworks allowed for ASIL D safety components. You don't try to fix a bad solder joint on a life-saving device. It's either mathematically perfect or it's garbage.
So to recap, the engineering team has designed a mathematically bulletproof architecture, they've armored the circuit board, and the factory has built it with 0 microscopic flaws. But before a single car equipped with this system is ever legally sold to a human being, the engineers have to actively try and destroy their own creation in a lab.
Welcome to the DVP&R phase. Design, Verification, Plan, and Report.
DVP&R, got it.
This is the ultimate torture test for production validation. The engineers have to empirically prove that every theory, every specification, and every perfectly torqued bolt we just talked about actually holds up in the real world under the worst possible combined extreme conditions.
And looking at the specs for these tests, they do not hold back. The first test detailed in the document sounds like a literal vibration and thermal hell.
It's heavily based on the ISO 17753 standard. They take the fully assembled, heavy control unit and bolt it firmly to a shaker table.
Okay.
This is an industrial machine that violently vibrates the unit in all three spatial axes, X, Y, and Z, simultaneously.
And they do this while running actual high voltage through it.
Yes, the unit is fully powered and operational,
Oh.
and while it is shaking violently, they lock it inside an environmental test chamber. This chamber rapidly and continuously swings the ambient temperature from -40 degrees Celsius, a deep, brittle freeze, all the way up to positive 125 degrees Celsius, which is significantly hotter than boiling water.
Wait, how long do they leave it in there?
They cycle this state of violent freezing and boiling vibration continuously for 500 hours.
That is 3 weeks of nonstop mechanical and thermal torture.
Yep.
What constitutes a pass? Like, what are they measuring?
During those 500 hours, there cannot be a single microsecond, not 1/1,000,000th of a second, of signal loss, network dropout, or voltage measurement error. If a single sensor blinks or drifts for a microsecond due to the heat or the shaking, the entire design fails the validation.
That is just the endurance test to see if it survives a lifetime of harsh driving. Next, they bring out the 50G sledgehammer to simulate the actual crash.
The mechanical shock test. After 500 hours of shaking, they subject the hardware to a physical half-sine shock wave peaking at 50 Gs of force for exactly 11 milliseconds. That kinetic profile perfectly simulates the brutal, instantaneous deceleration of a catastrophic high-speed vehicle impact against a solid concrete wall.
And the very moment after they smash it with 50 Gs, they trigger the crash signal to see if it still wakes up and discharges the high voltage in under 1.5 seconds.
Exactly. It has to survive the massive kinetic hit and then immediately perform its duty flawlessly, whether the chamber is currently at -40 degrees or positive 125 degrees.
Okay, those are incredible physical tests. But the final validation test in this document, this one is like something out of the Matrix. It relies heavily on HIL testing, hardware in the loop. Can you explain what this setup actually looks like in the lab?
Imagine a massive industrial dyno cell. They take the vehicle's electronic control unit and physically wire it to a real massive electric vehicle motor.
Okay.
That motor is bolted to a dynamometer, a huge machine that can forcefully spin the motor under extreme physical resistance. It's essentially a flight simulator, but for physical hardware.
So they have the real computer talking to the real motor, and the source says they spin this electric motor up to a screaming 12,000 RPM at absolute full electrical load. Everything is incredibly hot. Everything is operating at maximum electrical stress. And while the motor is screaming at 12,000 RPM, the engineers essentially hit the digital self-destruct button.
They inject a digital crash signal into the computer's network, but they don't stop at just simulating a normal crash. Through the HIL software interface, they simultaneously inject a barrage of catastrophic, cascading physical failures.
Right.
They digitally tell the system you've crashed into a wall and your main high-voltage battery relay has just welded shut and your primary physical discharge resistor has just snapped in half.
So they are lying to the computer, telling it that it is currently in the absolute worst-case scenario from failure mode 3, all while the physical motor is still spinning at maximum capacity. What is the computer expected to do with that nightmare?
It has to prove its ultimate autonomous intelligence. Within exactly 60 milliseconds of that digital chaos being injected into the system, the safety management unit must process the data, recognize that the voltage isn't dropping, deduce that the physical resistor is broken, instantly pivot its strategy, abandon the primary discharge plan, and trigger the stator copper loss backup plan.
It takes all that trapped lethal energy from the battery and violently dumps it back into the massive copper coils of the motor that is currently spinning at 12,000 RPM.
Yes. It forces the voltage down to under 60 volts in less than 2 seconds, entirely through complex software modulation of the magnetic fields, without blowing up the physical motor and without causing the dynamometer to violently seize up and destroy the multi-million-dollar test cell.
That perfectly synthesizes the sheer scale of paranoia, testing, and brilliance required to ensure passenger safety in an EV. We've traced this journey from physical wires shearing off to metal switches melting together to quartz crystals shattering inside microchips. And the response from the engineering world is to build a 100 microsecond reflex loop, use the copper motor coils as a giant emergency heater, obsess over solder bubbles down to a 1% margin, and violently shake the hardware for 3 weeks straight while boiling it.
It fundamentally changes how you look at the car parked in your driveway. There is literally an invisible army of mechanical, electrical, and software engineers riding shotgun with you every single time you press the accelerator.
Yeah.
They are sitting there ensuring that if the absolute worst-case kinetic scenario happens, this complex 2-second invisible electrical war is thought and conclusively won before your brain even fully processes that the car has hit a wall.
It really does, because when you look at an X-ray of a broken arm, it's clean, it's intuitive, it's either broken or not broken. You can see the mechanics of it. But the safety systems we've explored today exist in a completely invisible, murky world of electromagnetism, microseconds, complex thermodynamics, and thousands of lines of code. Yet they engineer it with a rigid exactness that rivals the physical steel structure of the car itself.
And the really exciting part is that this invisible world of software-defined safety is only going to get deeper and more complex. There's a fascinating, easily missed detail buried right at the very end of our source notes today that really points to where this entire field is heading.
Oh, what details stood out to you?
The author of the document casually mentions that they are now using highly advanced Python simulations to dynamically model the transient heat of the copper motor coils during that emergency stator copper loss discharge.
Okay, so they're modeling it on a computer.
Right, they aren't just relying on basic physics equations anymore. They're using complex software to perfectly map in 3 dimensions exactly how the physical metal heats up under immense sudden electrical stress in real time.
So they're simulating the exact real-time physics of the failsafe while it's happening.
And if we extrapolate that to the bigger picture, if engineers can perfectly digitally model how the powertrain's physical properties change under extreme electrical and kinetic stress, what happens next? Could future electric vehicles use artificial intelligence and real-time software simulations during the milliseconds of a crash, not just to trigger a safety switch to drain voltage, but to dynamically alter the physical structural properties of the entire powertrain?
Wait, like using the massive magnetic fields inside the motors to actively lock up or brace the physical structure of the car for an impact, adjusting on the fly based on where the impact is coming from?
Exactly. We are transitioning from a century-old era of purely physical crumple zones, where we just designed dumb metal to bend and fold in a predetermined way, into a completely new era of digital crumple zones, an era where software, sensors, and intense magnetic fields act as an active, intelligent, shape-shifting shield.
Digital crumple zones. That is an incredibly wild thought. The idea that invisible code and magnetic fields become a literal physical shield between us and a kinetic crash, well, that is absolutely something to mull over the next time you silently accelerate onto the highway.